This lecture is on the fundamental theorem of calculus, FTC for short, and it is used to evaluate definite integrals. We learned that definite integrals are the area under a curve, and that's fine if it's an area that you can solve using a geometric formula like that for a triangle or rectangle or something simple. But what about if it's a more complicated curve? Now, this theorem is generally proven using the mean value theorem, a proof I'm not going to show here. The idea is that to find the solution to this definite integral, to evaluate it, you go from f prime to f, which means implies you're anti-differentiating. So we take the antiderivative of the integrand, the quantity here, and then we plug in the upper limit, so we have f of b, minus plug in the lower limit, f of a. So you take the antiderivative, plug in the limits, and subtract them. So let's say we want to find the integral from 0 to pi of sine x dx. So basically we want to find this area under half a period of sine. So you take the antiderivative of sine, so you get negative cosine. We want to go from 0 to pi. I'll factor out the negative, and I plug in the upper limit minus plug in the lower limit. And then we evaluate cosine pi, cosine 0. Cosine pi is negative 1, minus cosine 0, so minus 1. So you end up getting exactly 2. So this area is 2. That's not an approximation. That is an exact value. The area under sine x from 0 to pi is exactly 2. One sort of rough way to look at this is the idea that this represents area under a curve. The integral symbol here, imagine you're adding everything up. F prime, that's a rise over run, and your dx is a run, so rise over run times run. The runs cancel, you get rise. So these are a bunch of little rises. So if you add up all the tiny little rises along this interval, you get the area under the curve. Now, sometimes anti-differentiating is very difficult, so we find other methods. Going back to, say, an absolute value, this is a case where we probably wouldn't try to anti-differentiate this because you need to figure out how to get two different equations anyway and then do them individually. It's easier just to draw it and realize that you have two triangles and find the areas of the triangles individually. Okay, here are now many examples. Integral from 0 to pi over 6 of cosine x minus 3x dx. So we have to anti-differentiate. Antiderivative of cosine is sine, minus antiderivative of 3x is 3 halves x squared. We go from 0 to pi over 6. So we plug in pi over 6. We get all this stuff. Minus, plug in 0. We get all this stuff. And then a lot of evaluation. Sine pi over 6 is a half. Minus, fix all that up. And then sine is 0, 0. This is all 0, so these are all zeros, luckily. And we get a common denominator. We get over to here, which is approximately 0.0888. But this is an exact answer here, 12 minus pi squared over 24. Now looking at this in terms of the calculator, what you can do is you put in for y1 the integrand, cosine x minus 3x, and then you find function integrate under the math menu, math 9. So function integrate of y1, because you put it in y1, comma x, comma 0, comma pi over 6. So what do you want to integrate is y1 with respect to what variables? That's x, from lower limit to upper limit, and you get 0.088. And as you can see, if I do this actually by hand, the 12 minus pi squared, and then divide it by 24, of course I get the same thing. And what's going on graphically is you're finding these areas in black. And of course, the area above the x-axis is positive, that below the x-axis is negative, and so net area is slightly positive. Okay, integral of rad x from 1 to 4. It's important to realize that rad x is x to the 1/2. So you add 1 to the exponent, so you get x to the 3/2, and then divide by the exponent. And dividing by 3/2 is like multiplying by 2/3. So remember, anti-differentiation is easier to use rational exponents. We're going from 1 to 4. Factor out the 2/3. Now plug in 4 minus plug in 1. And 4 to the 3/2 is 8. 1 to the 3/2 is 1. And so the exact area under this curve is 14/3. Okay, over here, 0 to 1 of 2t minus 1 squared. Multiply the whole thing out, so FOIL it, and then integrate term by term. This is all using power rule. And then we plug in 1, minus, we plug in 0. Luckily, these all go to 0. Figure out what all that is, and you get 1/3. This method down below is something called U substitution, which you learn a little bit later. Okay. -2 to -1 of u minus 1 over u squared. And so I'm going to rewrite the 1 over u squared as u to the -2. It makes it easier to visualize how to use power rule. So the u becomes a half u squared. U to the -2 becomes u to the -1 over -1, but the -1 cancels with this negative, so it becomes plus u to the -1. Plug in -1 minus, plug in -2, and then you've got to simplify all that, and after you do all the arithmetic, you get exactly -2 for that area. Okay, a case like this, before trying to integrate it, that is, before trying to anti-differentiate it, it's best to divide term by term. So u over rad u is u to the 1/2. 2 over rad u is u to the -1/2, or 2u to the -1/2, and that's a minus in there. And now we integrate using the power rule. So we add 1 to the exponent and divide by the exponent. So u to the 3/2 divided by 3/2, which is like multiplying by 2/3. Add 1 to the exponent, so we get u to the 1/2, and divided by 1/2 is going to give you 2 times 2, so that'll be a 4 there eventually. Still going from 1 to 4. I plug in 4, minus, I plug in 1, and then go through and simplify it, and you get exactly 2/3. Not an approximation, it's exact. Okay, power rule again. Add 1 to the exponent, and divide by the exponent. Factor out the 3/4. Now plug in 3, minus, plug in -3, and this ends up being 0. These cancel out. Now, v to the 1, this function, v to the 1/3, actually looks about like this. And this is an odd function, and so it makes sense that your overall integral will be 0 because all of this area cancels with all of this area because you're symmetric about the origin, since it is in fact an odd function. Okay, an absolute value situation, 0 to 3 of absolute value of 2x minus 3 dx. I factor out the 2 because it helps me realize where the vertex is of this absolute value, and then you plug in 0, plug in 3 to get these points, and I draw straight lines. So I've got 2 triangles times half times base times height. So 2 times half, the base is 3/2, and the height is 3, so you just get 9/2. So that's the non-calculus way to do it, which is much easier. Okay, some trigonometry. Integral of 1 is x. Integral of sine is negative cosine. And now we plug in the upper limit, minus, plug in the lower limit, and evaluate all of this. And we end up getting exactly pi plus 2. Okay, what I'll do first is put the 4 out front because it's a constant multiple, so let's ignore it for a little while. The integral of secant tangent is just secant, so we'll get to that down here. But the point I'm making in here is that secant is even, tangent is odd, so together it's an odd function. You're going from negative pi over 3 to pi over 3, so we know the answer should be 0 when we're done, assuming, of course, that we didn't go over any asymptotes, and I don't think we did in this interval. So now we bring the 4 out, plug in pi over 3, so secant's 1 over cosine, minus, plug in negative pi over 3, and those cancel out, and you get 4 times 2 minus 2, so 4 times 0 is equal to 0. Okay, this is a differential equation which we're always going to solve from now and for months by separation of variables. So I'll move the dt to the right, and now I integrate both sides. The integral of dv, and then I got the integral of this large quantity. I'm going from 0 to 3. That's part of the problem. And so integral of dv is just v. We don't have to worry about a constant integration. It's a definite integral over here. Bring the 10,000 out front. Integral of t is half t squared, minus integral of 6 is 6t. Go from 0 to 3. And we've got our 10,000. Plug in 3. If you plugged in 0, you just get 0. And so we have an overall negative 135,000. So in the context of the problem, it's a $135,000 loss. Okay, this problem here, to integrate this one, you want to distribute the rad x. So that's the most important thing to get you started. It's x to the 1/2, so you get 3x to the 1/2 minus x to the 3/2. And then we integrate using the power rule. So I've got 2/3 x to the 3/2, and then again, this will become x to the 5/2. And when you divide by 5/2, it's like multiplying by 2/5. So 2/5 x to the 5/2. Plug in 0, plug in 3. So we get all of this, and whatever that comes out to would be your answer.